Hello everyone, myself K. Vanisri, lecturer in physics, TTWRDC Women Siricilla. So as in the part of online lecture activity, I am going to give a lecture on statistical mechanics. I am going to give a lecture on statistical mechanics. Statistical mechanics is one of the branch of physics which is advanced theory of thermodynamics. Means it is outcome of the thermodynamics. So thermodynamics it is a classical approach which will explain only about some systems, only about macroscopic systems only will get the information from thermodynamics. But if we go for atomic level particles or microscopic particles, we didn't get any information by using thermodynamics. Hence, the statistical mechanics is introduced. Let us see, in this video lecture, I am going to cover these topics. First one is a brief description about thermodynamics. Means what are the failures of thermodynamics, for what systems it is applicable, for what systems it is not applicable. We can see in this slide. And the next one, introduction to statistical mechanics. So in this slide we can see the significance of statistical mechanics, what is the use of statistical mechanics. Next we have microstates and macrostates, what is mean by microstate, what is mean by macrostate, everything we will see in this slide. Next, one important tool of statistical mechanics is that ensemble theory. So ensemble is one of the important tool of statistical mechanics. By using this concept, we can simplify the complicated systems into simple. Okay, next one is classification of statistical physics. So till now we know that thermodynamics is completely a classical approach. Completely a classical approach means that is applicable only for the macroscopic bodies. Macroscopic nature only we will obtain from the thermodynamics. Not at all atomic level properties will not studied from the thermodynamics. So that's why statistical physics will give the macroscopic nature, at the same time microscopic nature. So how it is classified, let's see in this slide. Classification of statistical physics. So it will be classified into three types. Those are Maxwell Boltzmann, BoseEinstein, and FermiDirac statistics. So that is next slide. And next one is phase space. Phase space, it is same like coordinate space in the normal Newtonian mechanics or classical mechanics. We know that coordinate space to represent any system's position or velocity or momentum, compulsory we require one coordinate space we want. Coordinate space is must and should. By using that coordinate space we can represent the position, what is the position of this particle, what is the velocity of that particle, every information can be obtained from the coordinate space. So how the coordinate space plays a role in the Newtonian mechanics, in the same way phase space is also plays the same role as coordinate space. Okay, next one is Lioli's theorem. So I will give the statement of Lioli's theorem. So that is one of the application of phase space. Let's see here. First point, first topic is a brief description about thermodynamics. So thermodynamics, it is the study of the effects of work, heat and energy on a system. So which will give the effects of work, heat and energy on the system or by the system. So it is concerned with the macroscopic changes and observations. Thermodynamics is completely will give the macroscopic nature. For example, if you take a gas container, for example, if you take any system which have more number of molecules or which have more number of atoms, so the thermodynamics will give the overall behavior of the system. Means what is the overall pressure of the system, what is the overall energy of the system, what is the overall entropy of the system, that's it. We will get the only the macroscopic behavior of the system only obtained from the thermodynamics. If you want to know about any particles information, if you want to know about any particles information, that is not possible from this thermodynamics. It will not give the independent particle information, it will give the overall information only. That's why it concerned with the macroscopic changes and observations, and it makes no assumptions about molecular or atomic structure of matter. So what atomic structure or molecular properties will not be get from the thermodynamics. Next, all the thermodynamic systems can be expressed in terms of four quantities. What are the four quantities? Temperature of the system. We can represent any system in these four quantities only. So it may be temperature of the system, internal energy of the system, entropy of the system, and heat. Okay, these are the four quantities we can represent any thermodynamic system. Okay. Next, introduction to statistical mechanics. So this subject which will give the relationship between the overall behavior of the system and the properties of the particles. So means overall behavior and macroscopic behavior, overall systems behavior with the properties of the particles will give the relationship between macroscopic properties and microscopic properties. Very simple. By using the statistical mechanics, we will get the macroscopic behavior in terms of microscopic behavior. So actually, statistical mechanics will give the microscopic properties also. Means this is not exactly give the actual motion of the particle, but we can investigate the most probable behavior of the particle. That is possible from this statistical mechanics. Okay, next term. Let us see the significance of statistical mechanics, how it is simplified. With this example, I will explain how the statistical mechanics is useful comparing with the thermodynamics. So we know that thermodynamics is completely a classical approach. I already told that. Means it is applicable for only macroscopic bodies, means which are observable, which are distinguishable. For that particles, for that systems only, thermodynamics will give the information. But if you take microscopic particles, if we want to know about microscopic particles, then what we have to do? So we know that we have one tool. What is that? Quantum mechanics is there. So quantum mechanics is used to study about microscopic particles. Already we know that. So to know about any microscopic particle, we can use the quantum mechanics. But according to quantum mechanics, if you want to know about any particle, you have to write the wave function for that particle. Understand? So if you want to know about any particle, we have to write the wave function for that particle. So first we have to write the wave function for that particle. Next we have to write the wave equation for that particle. From that we have to solve the position, momentum and velocity, energy, whatever the physical properties are there. We can find out from all these can be find out from the wave function only. Means if you have the wave function, then only we will get all these information. This is total only for one particle. But if we have 1 mole of gas, 1 mole of liquid, see here, one example is here. So I am taking one liquid which has the 1 mole of liquid is there. In that, how many particles are there? In 1 mole of liquid, in 1 mole of matter, according to Avogadro number, there are 6.023 into 10 power 23 particles are there. According to Avogadro number. So how many particles are there? In 1 mole of liquid, it has 6.023 into 10 to the power of 23 particles are there. So according to quantum mechanics, if you want to know about one particle only, you have to write the wave function for that particle. But here we have the 10 power 23 particles are there. To know about this 10 power 23 particles, how many wave functions we have to write? We have to write 10 power 23 wave functions. From that wave functions, we have to write 10 power 23 wave equations, and we have to solve that 10 power 23 wave equations, and from that we will get the position, velocity and momentum of all these 10 power 23 equations. Is it possible to solve 10 power 23 equations? This is only for 1 mole. If you take 2, 3, 4 moles of matter, then what? then how we can do all this? So it is very, very difficult to solve these many problems, 10 power 23 problems. Hence, statistical mechanics is introduced. So statistical mechanics will solve the problem. If you see here, we have 10 power 23 particles are there. Kada? So in that particle, some of the particles will have the same properties, same macroscopic properties. Some of the particles will, here particle is considered as system. Some of the systems has the same properties. What are the same properties? Macroscopic properties. What properties? Macroscopic. Means some of the systems have the same pressure, same temperature, same energy. Some of the systems have same properties, macroscopic properties. But those are in different microscopic properties are there, but macroscopic properties are same. Which systems has the macroscopically same properties? Which systems has the macroscopically same properties? That systems are combined into one group. That one group is called as one ensemble, one problem. So here all these systems, all these particles separated into groups of systems, and this 10 power 23 problems can be reduced into somewhat less problems. So like that, statistical mechanics can simplify the number of problems. So it will works as that's why statistical mechanics will explains about the macroscopic nature in terms of microscopic properties. So hence statistical mechanics works as the bridge between classical mechanics and quantum mechanics. We know that classical mechanics completely macroscopic behavior. It will explain about macroscopic behavior, means the particles, the bodies which are observable, which are distinguishable only for that particles only, we will apply the classical laws. Classical laws or Newton laws or mechanical laws, all are applicable for macroscopic bodies only, not for microscopic bodies. But quantum mechanics, it is applicable only for microscopic particles. For atomic level particles only we will apply quantum mechanics. But here statistical mechanics, it works as the bridge between classical and quantum statistics. Means it will give the information about macroscopic bodies in terms of microscopic properties. Ante this will explain about macroscopic nature and also microscopic, both natures, both information will be obtained from the statistical mechanics. Okay, now next one. So in the previous slide, we have one discussion on microstate and macrostate. What is mean by microstate and macrostate? Microstate means the state of the individual particle, It may be position, it may be velocity, it may be momentum. Microstate represents the state of the individual particle. Particles position or particles momentum, all these comes under microstate. Then what about macrostate? Macrostate refers to the state of the whole system. State of the whole system means whole system information. What is the whole system pressure? What is the whole system energy? Not individual particle. It considered as whole system information. That is called as macrostate. Macro means large, micro means small. Microstate means will give the information of individual particle. Particles information. Macrostate means overall systems information. Okay. So, but the number of microstates, finding of number of microstates is somewhat difficult experimentally. Experimentally, we didn't find a number of microstates because in any many number of systems, many number of particles are there. So, if we have large number of molecules are there, then it is very difficult to find out experimentally about microstate. But we can find out the probability of number of microstates. So this is called as thermodynamic probability. Next we have ensemble, theory. Already I told that statistical mechanics, which uses the most important tool, that is ensemble theory. So we know that the group of particles, if we take a gas container, in that group of particles is called as system, group of particles is called as system or assembly, or group of systems is called as ensemble. Group of particles or collection of particles is referred to as a system. Collection of systems is called as ensemble. Okay. So which type of systems are collected? So for example, I already told that. So in this example, we have some oval shaped ensembles are there. Oval shaped structures are there. These are called as ensemble. These are, I am assuming that these are ensemble. So how the ensemble is created, how the ensemble will simplify the problem. Let's see from this diagram. So for example, each and every first ensemble, first oval shape ensemble, if you see there, how many particles are there? Particles nothing but here systems. How many systems are there? There are 5 systems. In the second ensemble, how many systems are there? 5 systems. In the third one also we have 5 systems. In the fourth one we have 6 systems are there. Totally how many systems are there? 21 systems are there. According to quantum mechanics, if you want to know about this system, this total gas container, you have to solve how many equations? 21 equations we have to solve. But here, by using this ensemble concept, this in the first ensemble we have 5 systems now. These 5 systems have the same macroscopic properties. These 5 systems have the same macroscopic properties, means that will macroscopically identical, means the same pressure, same energy, same entropy. These 5 systems have the same type of macroscopic nature, and in the second ensemble also that 5 systems have the same type of macroscopic nature, and remaining 5 systems have the same macroscopic nature, and whatever the bottom 6 systems, bottom ensemble, in that we have 6 systems are there, that will have the same macroscopic nature. Which systems are macroscopically identical? That all the systems are combined to form a group. That group is called as ensemble. I think you understand. Ensemble means it is a group of systems. In that group of systems, all the systems are macroscopically identical, but microscopically all the systems are different. So in the first system, 5 systems are there. They are macroscopically identical, but they are microscopically independent. Every system has different position, different momentum, different velocity. Microscopically all the systems are different, but macroscopically all the systems are same. Means same energy, all the systems have the same energy. Okay, so this type of group is called as ensemble. Ensemble is nothing but collection of systems. Collection of systems which are macroscopically identical. Collection of systems which are macroscopically identical but microscopically independent. Macroscopically identical but microscopically independent. So according to quantum mechanics, we have here 5, 5, 5, 6, total 21 problems are there. But according to ensemble theory, we have how many problems are there? First 1, 2, 3, 4. 4 ensembles are there, means 4 problems are there. Means total 21 problems reduces to 4 problems. Solving of 4 problems is easy than comparing with 21 problems, isn't it? Solving of 4 problems it is easy to solve 4 problems. So like this, statistical mechanics simplify the difficulty in solving of any number of systems. So that's why this ensemble has the application about large number of particle systems. Okay. Next, how these ensembles are classified. Let us see the types of ensemble. So there are 3 types of ensembles are there. So depending on the exchanging of energy or exchanging of particles with the surroundings, there are 3 types of ensembles are there. Those are microcanonical ensemble, canonical ensemble, and grand canonical ensemble. So let us see, first one is microcanonical ensemble. So microcanonical ensemble, in this figure if you see, all the systems are separated with all the systems have the same energy, same volume and number of particles. So here in the systems it represents capital E, V, N. E means energy of the system, V means volume of the system, N means number of particles in the system. Every system has the same energy, same volume, same number of particles. Ante macroscopically all these systems are identical. That's why this is considered as one ensemble. Understand? So ee mottam black ni we will consider as one ensemble because all the systems have the same properties, same macroscopical properties. What are the macroscopic properties here? Energy E, volume V, number of particles N. These are the macroscopic properties. Okay. So all these systems are separated by rigid, impermeable and well insulated walls. Rigid means there is no chance of transformation of particles from one system to other system. Impermeable, that is no permission for the particles. No permission for the particles. Particles cannot exchange from one system to other system. And well insulated, all the systems are well insulated. Here black cross lines are there na, that represents the insulating insulating behavior. Well insulated means there is no exchange of temperature, there is no exchange of energy. Okay, so completely completely these are not exchange any energy or volume or number of particles with the surroundings, with the other systems. So that's why microcanonical ensemble, it is related with the isolated system as per the classical approach. Is in the classical approach we have a isolated system, open system, closed systems are there. This microcanonical ensemble is relates with the isolated system. This is one of the important point here. So in according to classical approach, microcanonical ensemble is treated as isolated system. It is treated as isolated system because no exchange of energy taken place, no exchange of particles taken place, volume is also constant. All the systems have the same macroscopic properties, not exchanging of anything. Okay, so next one is canonical ensemble. So canonical ensemble, it is the collection of independent assemblies which have the same temperature T, volume V and number of identical particles N. So see here in this figure we have a temperature. All the systems have the proper parameters like temperature T, volume V and N is the number of particles. All are separated with the rigid, impermeable but diathermic walls. All these individual assemblies, individual systems are separated with the rigid. Rigid means not those are strong. So and impermeable, not exchanging of particles. Impermeable but diathermic walls. Diathermic walls means there is no insulation. The energy can exchange from one system to other system. The temperature can exchange from one system to other system. Up to which point the temperature can exchange? Temperature means the heat can exchange. Means up to all the systems come to common temperature. Up to that time all the systems can exchange the heat energy. So here in this canonical ensemble only energy can exchange but not number of particles, but not volume. So canonical ensemble in this ensemble only energy can exchange and this system can be treated as closed system as per classical approach. As per classical approach, this canonical ensemble is treated as a closed system. In the closed system only energy can exchange. Up to which limit energy can exchange? Up to all the systems come to common energy, common temperature వచ్చేంత వరకు they can exchange the temperature. Okay. So this canonical ensemble can exchange only energy but not particles. Particles will not exchange in the canonical ensemble because all these systems are separated with impermeable walls. Na? Impermeable ante there is no chance of exchanging of particles. Next we have grand canonical ensemble. So grand canonical ensemble, in the figure, if you see, all the systems have the same temperature T, volume V, and chemical potential mu. Here we have one new term. What is that? Chemical potential. What is mean by chemical potential? So chemical potential is nothing but the change in free energy when we add a substance, when we add a 1 mole of substance to the system. So you know that chemical potential means a concentration of the system will be changed when we add some external material, external matter. So if we add external matter into any system, then what happened? The concentration of the system will be changed. The concentration of the particles, the concentration of the matter will change. If the concentration changes, automatically the energy will change. So this represents the change in energy due to the adding of substance externally to the system is called as chemical potential. Understand here? Chemical potential means the change in free energy by adding of externally, by adding of 1 mole of substance to that system is called as chemical potential, and this adding of substance will be taken at constant pressure and constant temperature. So this is called as chemical potential. Chemical potential is nothing but change in free energy when we add 1 mole of substance to the system at constant temperature and constant pressure is called as chemical potential. So let's see here what is mean by grand canonical ensemble. In this grand canonical ensemble, all the systems have the same temperature, volume V, and chemical potential mu. Chemical potential represented with mu here, and all the systems are separated with rigid. All the systems are separated with rigid, permeable and diathermic walls. Permeable means there is a chance to exchange of particles taken place here. There is a chance to exchange of particles. And diathermic walls, and so there is a chance to exchange of energy. In the case of grand canonical ensemble, the energy can exchange and number of particles also can exchange. So this is treated as open system. As per the classical approach, grand canonical ensemble is treated as open system. Open system ante enti? In that open system, that system can exchange energy, the system can exchange particles. So in this system, in this ensemble, the system can exchange number of particles and it can exchange energy. Up to which limit? Up to all the systems come to same temperature and all the systems come to same chemical potential. Till that point, the exchanging of number of particles and energy exchange will take place. Okay, so next we have classification of statistical physics. Till now we know that I already told that thermodynamics is completely a classical approach. Thermodynamics is completely a classical approach, means that is applicable only for macroscopic bodies only. It will not explain about microscopic nature. But statistical physics have the two classifications are there. It is divided into two types. First one is classical statistics and quantum statistics. Second one is quantum statistics. Classical statistics is developed by Maxwell Boltzmann. Maxwell and Boltzmann, though they were the scientists who developed the classical statistics. And quantum statistics, this is developed by BoseEinstein and FermiDirac. So quantum statistics again divided into two types: Bose-Einstein statistics and FermiDirac statistics. So classical statistics, it is applicable for distinguishable particles only, and on the particles there is no restriction. So any particle can occupy any energy state. Quantum statistics, we have two types: Bose-Einstein statistics are there, FermiDirac statistics are there. So in this case, quantum statistics, all the particles are identical particles and indistinguishable particles. All the particles are identical particles and indistinguishable particles. But in the case of Bose-Einstein statistics, there is no restriction. means any particle can occupy any energy state. There is no restriction. But in the case of Fermi-Dirac statistics, so in this case all the particles are identical, indistinguishable, but have restriction. Every state can occupy with only one particle. Let's see in the next slide. We will see what are the conditions of Bose-Einstein statistics and Fermi-Dirac statistics. Let's see here. First one is classical statistics. So classical statistics, this is accurately, successfully explained about macroscopic phenomena such as temperature, pressure, energy, etc. So classical statistics successfully explained about macroscopic phenomena. So about temperature of the system, it will give the clear information about the pressure of the system, about energy of the system. All these macroscopical phenomena are explained successfully by classical statistics, but it is failed to explain about some experimental phenomena such as black body radiation, photoelectric effect, specific heat at low temperature. So these are the quantum mechanical concepts. Actually, black body radiation, photoelectric effect, and specific heat, all these are comes under quantum mechanical concepts. So all these concepts are not explained by classical statistics. Classical statistics does not explain these experimental proofs. What are the proofs? Black body radiation is not explained, photoelectric effect, and specific heat. So for that, the failure of classical statistics leads to the failure of this classical statistics leads to the development of new statistics, that is quantum statistics. Okay. So classical statistical mechanics failed to explain about black body radiation, photoelectric effect, specific heat at low temperatures, and Compton effect. All these quantum mechanical concepts not explained by classical statistics. Hence, a new statistics is introduced, that is quantum statistics. So it will explain all the experimental quantum mechanical experiments like all these black body radiation, photoelectric Compton effect, photoelectric effect, all these are explained by quantum statistics. Okay, so classical statistics explained by Maxwell Boltzmann statistics, Maxwell Boltzmann. So that's why this is also termed as Maxwell Boltzmann statistics. Okay. Let's see. So in the Maxwell Boltzmann statistics, how the particles are distributed in the energy states. Let's see here. So already I told that classical statistics is applicable for distinguishable particles. It is applicable for macroscopic bodies, means distinguishable particles. Okay. So in this classical statistics, how the distinguishable particles are arranged in the energy states. How many ways are there to distribute the particles in the energy states? Let's see here. For example, I am explaining here with an example the distribution of particles in energy levels. Let us take the number of particles is 2. The number of particles is 2. So n is equal to 2 I am taking here. And what are the two particles? Capital A and capital B. Why I am taking here different particles A and B? Because classical statistics applicable for distinguishable particles. Particles should be distinguishable. We can identify the difference. A and B. These are the two particles we are taking. Now we have to arrange these two particles in the two states. How many states are there? Energy states are there. 2 states are there. We have to arrange these two particles in the 2 states. How many ways are there? Assume here how many ways are there. How many ways you can arrange these two particles in the 2 states. Ela arrange chestam manamu? In the first you see here green boxes are there. Horizontally we have two boxes are there, means 2 states. These are considered as 2 energy states. So in the first case A particle is occupied in the first energy state and B particle is occupied in the second energy state. In the second case, in the second way, this is called as second way. In the second way, first B particle occupied in the first state and A particle occupied in the second state. In the third way, we can also have one more way, one more chance is there. Both particles can occupy in the first state, and second state is empty. And last way, both particles can be occupied in the second state, first state is empty. So why this taken here? Two particles can occupy in one state, two particles are occupied in one state, because there is no restriction in the classical statistics. Classical statistics లో ఎలాంటి restriction లేదు, because classical statistics does not obey Pauli's exclusion principle. Pauli's exclusion principle. What is mean by Pauli's exclusion principle? Pauli's exclusion principle is nothing but any any one particle doesn't have same quantum numbers. Any two particles does not have same quantum numbers. Any two particles does not have the same quantum numbers. Okay, so here any number of particles can occupy one state, because there is no restriction in the classical statistics. It is applicable for macroscopic bodies which are distinguishable. There is no restriction because it's not depends on Pauli's exclusion principle. What is Pauli's exclusion principle? No two particles have the same quantum number. Okay, so how many ways are there? The distribution ways, there are four ways are there. Four ways. We can distribute the particles in four ways. Let us see, if we have only two particles, then we have the four ways are there. If we have three particles, then how many ways are there? If you take three particles in two states, you can distribute like this. First state, we can take two particles. In the second state, one particle. Like that, we have so many ways are there. So the general formula to find out the number of ways of distributing the particles in the energy levels is, general formula is G power n. General formula is G power n. What is capital G? G is called as state, energy state, and n is the number of particle. Okay, ikkada we have two particles and two states. That's why 2 square. 2 square means four ways are there. Four ways are there. If you take three particles and two states, then how many possible ways are there? Then you have 2 power 3 means 8 ways are there. 8 chances are there. 8 types. We can distribute the three particles in two states. How many ways? 8 ways. Depending on this formula G power n, you can find out the number of ways of Maxwell Boltzmann distribution. So number of ways of distribution of particles in energy levels. Okay, so G power n, G is the number of energy states and n is the number of particles. Okay, I think you understand this one. You can take other examples also. Next, we have quantum statistical physics. Quantum statistical physics. Already I told that classical statistics failed to explain about some experimental phenomena such as black body radiation, photoelectric effect, and specific heat. I already told that these are the quantum mechanical concepts. These are not explained by classical statistics. Hence, quantum statistics is introduced. So quantum statistics, it is applicable for indistinguishable particles. It is applicable for indistinguishable and identical particles. And this quantum statistics is subdivided into again two types. Quantum statistics is subdivided into two types. One is Bose-Einstein statistics and other one is FermiDirac statistics. Bose-Einstein statistics and FermiDirac statistics. Bose-Einstein statistics is developed by Bose and Einstein, and FermiDirac statistics is was developed by Fermi. He was the scientist, and Dirac also he was the scientist. Fermi and Dirac developed this statistics. That's why it is called as FermiDirac statistics. And Bose-Einstein statistics, let us see here. This is applicable for only bosons. Bose-Einstein statistics is applicable for bosons. What are the bosons? Bosons are the particles which have the integral spins, like 0, 1, 2, 3 and so on. Okay, so bosons are all quantum particles. Those are identical particles, are indistinguishable particles. Examples for bosons are photons and helium atoms. Photon nothing but light particle. and helium atom nothing but alpha particle anamata. So alpha particle. So bosons have the integral spins like 0, 1, 2, 3 and so on. So Bose-Einstein statistics is applicable for only bosons. In this statistics, all these particles should be identical particles and indistinguishable particles. Here third condition is that any number of particles can occupy a single cell. In the case of Bose-Einstein statistics, any number of particles can occupy a single cell. Single cell means Bose-Einstein statistics does not obey Pauli's exclusion principle. Pauli's exclusion principle not obeying here, because here also identical particles, even though bosons will not obey the Pauli's exclusion principle, means any number of particles can occupy one single state. Okay, so let us see how the particles are distributed in the energy state. How the particles are distributed in the energy states. Let's see here. I am taking, for example, I am taking 3 particles are there here. So 3 particles, all particles are identical particles and indistinguishable particles. Here I am taking 3 particles. All these 3 particles are same particles. What are the 3 particles? Capital A. I am taking the same particles because bosons nothing but identical particles. Now identical means all the particles are same. So A, 3 particles are there, and how many states I am taking here? 2 is the number of states. 2 is the number of states. Now I am taking 2 states, 3 particles. 3 particles are there, 2 states are there. How you distribute the 3 particles in 2 states? So 3 particles ni 2 states lo distribute cheyali. Ela cheyali? Let's see, first case 3 particles in first state and second state is empty. This is one way. Second case lo 1 particle in one state and 2 particles in other state. This is one way. And third case, 2 particles in first state and 1 particle in second state. This is third way. Next, last way, first state is completely empty and second state completely filled by 3 particles. So these are the 4 ways are possible. Is there any other way? Is there any other way to distribute the particles? Only we have 4 ways. 4 ways is possible. Only 4 ways are possible to distribute 3 particles in 2 states. How you can find out this general formula? Because if we have only 3 particle 2 states, then we can easily tell how many ways are there. But if you have n number of particles, some 50 particles are there, some 50, some 25 states are there, then how many possible chances are there? How many possible ways are there? It is somewhat complicated. Then to simplify that problem, here we have the general formula for the distribution of bosons, for the distribution of particles in the energy states for Bose-Einstein statistics is given as n plus g minus 1 factorial by n factorial into g minus 1 factorial. N means number of particles, G means number of states, minus 1 factorial by n factorial into G minus factorial, G minus 1 factorial. For here we have 3 particles are there, 2 states are there, means 3 plus 2 minus 1 factorial by 3 factorial into 1 factorial. Totally how many ways we get? 4 ways are there. But if you take 5 particles are there, and 3 states are there, then can you tell how many ways are there? So there are 5 particles and 3 states. 5 plus 3 totally 8 minus 1. 8 minus 1 means 7 factorial by 5 factorial into 5 minus 3, 2 factorial. So by cancelling all this, you will get the number of ways of distributing the particles in the energy states. Okay, so next we have FermiDirac statistics. So FermiDirac statistics, it is applicable. It is also a quantum statistics. It is applicable for identical and indistinguishable particles, and in this case one important restriction is that, so in the Fermi-Dirac statistics, only one particle can occupy only one state. One particle can occupy only one state. Not more than one particle can occupy in single cell. No more than one particle in a single cell. ఓకే. సో అంటే ఒక సింగిల్ సెల్లో వన్ సెల్లో ఓన్లీ వన్ పార్టికల్ మాత్రమే ఆక్యుపై చేయాలి. 2 or more particles cannot be occupied in a single cell. That is FermiDirac statistics. Fermions obeys the Pauli's exclusion principle. What is Pauli's exclusion principle? So no two particles have the same quantum numbers. No two particles have the same quantum numbers. Means one particle, according to that Pauli's exclusion principle, these fermions can occupy in only one single cell. No two fermions in one single cell is not possible. Okay, no two fermions in one single cell. So all these particles, these particles have half integral spins. Half integral spins means 1 by 2, 1 by 2 h cut, 3 by 2 h cut, 5 by 2 h cut, or minus 1 by 2, plus or minus half integral spin, minus 1 by 2 h cut, minus 3 by 2 h cut, minus 5 by 2 h cut. Like that, all these fermions have the half integral spins, and these particles which are obeying FermiDirac statistics, that particles are called as fermions. That particles are called as fermions. What are the examples for fermions? Fermions are electrons, protons, and neutrons, etc. So many fermions are there. All these particles have the half integral spins and asymmetric wave function. So and all have the half integral spins. Next, let us see the distribution of particles. The distribution of particles in energy states in the FermiDirac statistics. For example, if we take two particles are there, all these two particles are same particles. I told already, FermiDirac statistics also, in this also particles are identical and indistinguishable. Rendu particles kuda identical particles and indistinguishable particles. Ante there is no difference between the particles. So that's why here the number of particles is 2. Those are A comma A, same particles, and number of states G is equal to 2. Then how many number of ways are there? Because here FermiDirac statistics obey Pauli's exclusion principle, means no cannot be more than one particle in a single cell. More than one particle in a single cell. Only one particle can occupy one cell. So that's why how many ways are there? There is only one way. Because two particles are there, two states are there. Two particles are occupied in the two states. How many ways are there? There is only one chance. One chance is there. Okay, so that's why FermiDirac statistics, in this case, the number of ways are very small. That depends on number of particles and number of states. Okay. So next one is Phasespace. This is one important concept in the statistical mechanics. Already I told that in the case of Newtonian mechanics or classical mechanics, if you want to know about motion of the body, if you want to know about any motion of the body, then we have to use coordinate system. We have to use a coordinate system. What coordinate system represents? Coordinate system represents the coordinates like x-axis, y-axis, z-axis. The three coordinates will be represented in the coordinate system. That will represent the position of the system, that represent the momentum of the system. The motion of the particle will be known from the coordinate system. In the same way, how the coordinate system plays the role in the Newtonian mechanics or classical mechanics, in the same way Phasespace plays the same role in the statistical mechanics. So here in the Phasespace, this concept is suggested by Gibbs. He was the scientist. He suggested that if you want to know about instantaneous state of a particle, so in a gas container, if we have so many number of particles are there, so if we want to know about instantaneous state of any particle, we can use this Phasespace concept. This is completely imaginary concept. Phasespace concept is completely a imaginary concept. It is a 6-dimensional space. Phasespace is the 6-dimensional space. In this state, 6 coordinates. In this space, 6 coordinates x, y, z, comma px, py, pz are marked along 6 mutually perpendicular axes in space. So here x, y, z represents the position coordinates, px, py, pz represents the momentum coordinates. The combination of position coordinates and momentum coordinates is called as phase space. Phase space is nothing but the combination of position space and momentum space is called as phase space. So phase space is the 6-dimensional space. So for example, if we represent the phase space for single particle, means single particle position, single particle momentum, if we represent with the phase space, then that space is called as mu space. Mu space is the individual single particle space. Mu space represents the single particle space, means single particle position components, single particle momentum components. But if we take a total overall system behavior, then overall system particles have different positions, different momentums are there. All these positions and momentums are represented on the phase space with the phase points. Let us see here. In this diagram, in this graph, S is the point. Let us assume S is the point that represents the instantaneous position, instantaneous state of any particular particle. Instantaneous state of the particle, and this point, so a point in the phase space representing the instantaneous state of the particle is called as phase point. What is meant by phase point? Phase point is nothing but a point in the phase space which represents the instantaneous state of the system, instantaneous state of the particle. Particle యొక్క present situation, present position ఎంత, present momentum ఎంత, that particular position and momentum represented with one point. That point is called as phase point. Phase space lo we have so many phase points are there. By combining all these phase points, you will get the phase trajectory, phase path. The path of the phase points is called as phase trajectory. Phase trajectory will explains about the all the systems instantaneous position and momentums all will be known from the phase trajectory. Okay. So next here we have one significance of phase space here, Liverley's theorem. Liverley's theorem, I will give the statement of Liverley's theorem. So statement 1, there are two proofs are there for Liverley's theorem. First one is the rate of change of density of phase point. The rate of change of density of phase point in phase space is 0. Here that is represented with the dou rho by dou t is equal to 0. Dou rho by dou t is equal to 0. What is rho here? Rho is the density of phase point. Rho, what is meant by rho? Rho means density of phase points. Density is constant, means at any instant of time in the phase space, if you take any instant of time, so this is the phase space, at any instant of time the density of phase points is constant. Means for example at initial time, for example let us assume phase points in the some region is 5. Understand? So one region, I am taking one region. In that region, how many phase points are there? 5 phase points are there. After 5 minutes also, in the other region, how many phase points are there? 5 phase points only. Means at any instant of time, the density of phase points is constant. The density is not changed. The density will be remains as constant. The density of phase point remains as constant at any instant of time. That's why dou rho by dou t is equal to 0, means density of phase points is constant. Rho is equal to constant. Next other proof, second one is delta d by dt of d of delta tau by dt is equal to 0. So d delta t by dt is equal to 0. The rate of change of temperature change, the rate of change of temperature change is equal to 0. The change in temperature is constant. The change in temperature is constant at any instant of time. So at any instant of time, if you see the region in the phase space, everywhere the temperature change remains constant. Temperature change remains constant. So for example, in the first instant of time, first 5 minutes low 5 degrees change in ankondi. Next instant of time, next 5 minutes low same. Next after 5 minutes చూస్తే కనుక again same 5 degrees of temperature will change. The change in temperature remains as constant. constant. So these are the two statements of Livolis theorem. This will have the proof, but I am not explaining here the proof. Okay, so this is about my lecture in the part of online lecture activity. Thank you everyone.